Screencast 18.5, Entropy. Entropy is basically a measure of the randomness of a process. And it might sound a little funny, but let us consider various systems and think about if the randomness is increasing, in which case the entropy would be going in the positive direction, or the opposite, getting more organized, giving us a negative value for delta S. Perhaps this originated with the Big Bang, where things have been getting more random, more spread out for our entire universe. It's just kind of a state function here since the beginning of time. Quite a thought there. Okay, liquid turns into a gas. Those molecules will start moving around with more freedom, a more random process. Delta S should be positive. A liquid turns into a solid. Things are getting more organized, like soldiers lining up. This is negative, a less random process. When you have a decomposition reaction, one particle breaks in half to become two, more random, entropy is increasing. These are all predictable, and this is basically how one can interpret or predict the entropic component of a chemical process. Let's go ahead and do a calculation. We've got a change in enthalpy and entropy happening at a certain temperature. These are designed so that they plug directly into delta G equals delta H minus T delta S, the free energy equation. And it's even set up so that you don't have to change your units. If this showed 145 kilojoules, you'd then have to change it. So watch out for this. If this was not Kelvin, you'd have to change it because the entropy value is joules per Kelvin. So make sure your units line up and then plug in. So it's simply 145,000 minus 382 Kelvin multiplied by 322 joules per Kelvin, giving us a positive value. That's what you really want to look at, is the sign of this value. This is a non-spontaneous process. This is Screencast 18.5.